Welcome, everybody. I am Alexander Kent. I'm the executive director here at the Robinson Film Center. It's a Monday night here at the movies, so you're doing the wrong thing. So thank you. Thank you very much for being here. We've been actually looking at, look at that thing. You're going to learn all about that thing tonight. We have been eyeing this Science on Screen program, which is a national program where art houses basically explore movies through science. Very, very simple concept. But tonight there's 23 theaters around the country, and we're one of them, that are showing 23 different films with at least 23 different scientists coming up to give us a way in. We obviously, if you read the title of our talk, we're obviously BuzzFeed readers. So I'm gonna prep you with that if you don't know it. It's how to chat about dark matter, supersymmetry, and particle physics on date night. So our guest this evening, Lee Sawyer, from Louisiana Tech. If we were going to talk about existential French literature or film noir, I can help you on date night. He can help you with this stuff. But he's also a film buff too, so I think this is going to be great. We're really proud of this program, and tonight is really just a kickoff of what we're doing. This is funded by the Sloan Foundation, a big national foundation, and the Coolidge Corner Theatre Foundation out of Brookline, Massachusetts, which is this wonderful, massive art house right outside of Boston. And I think what we're going to do in May is we're going to take about a 6-week break, and then we're going to show as many films as we possibly can in May with a science talk with it. So one of the ones that we have, we're going to do Big Hero 6 and do robotics. We just talked about possibly doing we're thinking about black holes on Interstellar maybe, or maybe Forbidden Planet. So we're all open for ideas, but we'll have this calendar probably firmed up in about 2 or 3 weeks. So we're going to have a whole month of this. Really important that we're going to be working with a lot of local partners. We're working with Louisiana Tech, we're working with Sci-Port, we're going to be working a little bit with Willis-Knighton. We're going to be working with a mental health advocacy group called NAMI. We're really proud that we're going to be able to, a place where people can come talk about science, and most importantly, see movies through a different lens. So we welcome you to this program. I will introduce our guest after the film. It's a short documentary. If you haven't seen it, it is absolutely fantastic. I think one of the reasons I'm so excited about this is that it's edited by a film legend named Walter Murch. The guy made Apocalypse Now, and he does a science doc, and I think that that's kind of the cool thing about this. So it's a really superbly made film, and I think you're going to enjoy it. We'll be back in about 100 minutes, and we'll talk about this film. So thanks for coming. This is great to see a full house. We're just getting started. Thank you. Okay, everybody. It's a little hot, so I want to introduce Dr. Lee Sawyer from Louisiana Tech, Director of Chemistry and Physics. He's not only going to talk about this film and what we need to know, but connect it to a university that's kind of the brain of Louisiana in a lot of ways. I think it's really remarkable that a story this big reaches out so far, and we're excited to hear what you have to say.
Thanks, Alex. What did you think of my experiment? Thanks for coming out. This is so cool. Monday night, and we got a full house of people interested in science, and I think that's terrific. I got to let you in on a secret. I actually didn't pick the name of the talk. Megan did, but I liked it, and I thought that's really cool. How would you talk about things like supersymmetry, dark matter, particle physics on date night? Before I get started, another big thanks to the Robinson Film Center. I love this place. As Alex said, I am. And I didn't realize until I was sitting here and I was watching the little trailer before where they were talking about the beginnings of science on the screen. And they were talking about the first time this was done in Brookline, Massachusetts. Melissa Franklin, we call her Missy. Melissa Franklin is on this experiment. So one of the first people who did the science on screen is actually on Atlas as well. And I've known her for several years. So so how do you chat about supersymmetry, dark matter, and particle physics on date night? Of course, you're much better at it now, having seen particle fever. You're ready to do this. So here's a couple of people. I think of her as a theorist, right? She's thinking about the Higgs potential and symmetry breaking. He's more the experimentalist, right? So he's thinking in terms of 5 sigma significances over there. So, well, let's get started. So they talked one of the things I want to do here, and I'm not going to talk a lot. I got 12 slides. Let's do a little Q&A. You can ask me some stuff. Mostly I just kind of maybe want to clarify some things that might be a little murky or you might not have understood. It's just particle physics, right? So it's pretty straightforward. But if there was anything in there, try to clear it up. So we have this thing called the Standard Model. The Standard Model was started to be developed in the 1930s, 1940s. A cool thing that you didn't catch. If anybody in here caught it, I'll give you $1. When they're showing the Institute for Advanced Physics in Princeton, which is where Einstein was, where Bacall, who was one of the great cosmologists of the 20th century, born in Shreveport. John Bacall was at the Institute for Advanced Study at Princeton as well. Where they're showing that scene in the Institute for Advanced Studies with NEMA, and they're trying to get the video going from CERN to watch the Higgs discovery. There's a very old man in the audience. That old man is Freeman Dyson. And Freeman Dyson wrote down the beginnings of the Standard Model. He and Dick Feynman and Tokunawa in Japan wrote down what we call quantum electrodynamics, the field theory that describes electromagnetic interactions. So it dates back from the 40s, and folks like Dyson and Feynman, and developed in the 60s and in the 70s, people like Higgs. It is the best tested theory mankind has ever come up with. It is a work of art. We have measured interactions of electrons and protons and neutrinos and muons to 6, 7, 8, 9, 10 decimal places, depending on the reactions. It is a beautiful theory, and we know it's incomplete. Isn't that bizarre? So, nature as we know it is made up of these things, these quarks, up, charm, down, strange, bottom. Everything we know is the up and down quark and protons and neutrons. I was on the experiment in the 1990s, 1995. We discovered the top quark at Fermilab. Electrons, heavy versions of the electron like the muon and the tau. This is the stuff that makes up matter. And then there are these interactions, and so particles like gluons, the photon that we know, light, communicates these forces between these particles. That's the Standard Model. This is sort of the new periodic table that we have these days. The Higgs is there in the middle, sort of holding everything together. Again, that's the particle that gives mass to everything that has mass in the Standard Model. So that's sort of the linchpin. We're talking a little bit about why we know it's incomplete. First of all, again, it is mathematically simple, as you can tell. If you go to CERN, you can get it. You can get the Standard Model Lagrangian on a T-shirt in the gift shop there. As Al said, make things as simple as possible, but no simpler. So we have this view now of nature, kind of going from right to left, where we have atoms. We used to think that was the most fundamental thing in nature was the atom. Then Rutherford, folks like that, in the early part of the 20th century, showed us that in fact the atom had structure. There was this nucleus. By the 1930s, we knew that the nucleus consisted of both protons and neutrons. In the 1950s, we discovered that protons and neutrons had a size, that they weren't point-like, but they had a physical size to them. In 1970, we started probing inside protons, seeing that there were things in there that would scatter stuff off, and those were the quarks. And so we've drilled down smaller and smaller sizes now, and in doing so, come up with this mathematical formulation to describe what we see. Again, what I do, I'm an experimentalist. I work on these huge experiments like the Atlas experiment at the Large Hadron Collider. We take bunches of protons, we smash them together. It's not protons on protons, so you might get a maybe a false idea of thinking about this. It's bunches. It's 10 to the 34th protons at a time colliding together. And every 25 nanoseconds. And every 25 nanoseconds, these protons are coming in together, they're interacting, and they're shooting things off, hopefully at large angles that we can detect inside of our experiment. One cute little thing about this, the watch there, is that we're allowed to violate the laws of nature as long as we don't do it for very long. It's something called the Heisenberg uncertainty principle. How do you make something heavy like a Higgs? And the way you do it is you can have an imbalance of energy as long as the time scale is very short. Heisenberg uncertainty principle says that you're allowed to do that. And then Einstein, E equals mc squared, says I can take energy, I can turn it into matter. E can equal mc squared, right? M, mass, E, energy. I can turn it into mass for a very short period of time and then let it decay away. So those are the two things we have going for us in these experiments. You've already kind of seen this before, bird's eye view. This is my home away from home. I spend part of my time in Ruston. I spend part of my time in Geneva. It's a strange life. That's Pontchartrain Airport in Geneva. That's Lake Geneva. You know the song by Deep Purple, right? We all went down. Okay. All right. So that's Montrose actually over on the other side. This is a 27-kilometer, 17-mile tunnel. Most of it's underground. This part over here actually goes under the Jura Mountains. These are the Juras. That's where the word Jurassic comes from. In fact, when they were doing this tunneling in the mid-'80s, they hit groundwater under high pressure, killed about 4 people in the tunneling crew. A lot of little villages. When I was there in the 1980s as a student, this was all cows and farms. This is growing up quite significantly now. The Swiss-French border goes. Hold on just a second. Where's the customs? Customs post right here. So the Swiss-French border goes right through here. And this is the little village of Ferney-Voltaire in France. This is Geneva, Mayrin in Switzerland. And so this is right on the border between France and Switzerland. That was done on purpose. CERN was created in the 1950s in the aftermath of World War II. This was a way to try to bring Europe back, bring European nations back together, have them work together. Switzerland had this long history, of course, of being a neutral nation. And one of the leading figures in developing CERN was an American scientist by the name of Rabi, I. Rabi, who was at Columbia University. His parents had immigrated from Hungary just before before World War I, in fact. And Rabi was influential in actually creating the European Center for Nuclear Research. It's now called the European Center for Particle Physics, but we keep the acronym. We still call it CERN. So once you have a good name, you don't lose it. It's like, sort of like Ezekiel's vision. It's rings within rings. Again, they didn't talk about this very much. Where does the LHC beam start? The LHC beam starts with a can of hydrogen. A bottle of hydrogen about this big is the beginning of the Large Hadron Collider beam. All right? And they take that hydrogen, they strip the electrons away, they begin to electrostatically accelerate it. They put it in a larger ring, and then a larger ring, and then a larger ring, and then the really big ring, and collide it. Atlas is here. It's just across the street from the main campus. There's a little gas station right there where you can buy sandwiches early in the morning if you're on shift. The other guys are way over here, suckers. CMS is way on the other side in the French countryside near a little village called Versailles. And so I think I'm on the better experiment here. You can stay on site and just walk over there. So you saw a couple of scenes from first collisions, but I wanted to stop the film and point out that gentleman right there is Ram Dulapudi from Louisiana Tech University, and he was there for first collisions when we were first colliding beams. On shift, looking at data quality plots there. Ram's now a postdoc down at LSU. They hire our guys to go down there and do their data analysis for them. So I had to get that in. Okay, so and this is actually a good friend of mine right here, Ricardo Gonzala from Portugal, and this is a good buddy of mine, Brian Peterson from Copenhagen. And I'm a kid who was born in Shreveport, Louisiana, grew up in North Louisiana. I never thought I would be able to stand in front of a bunch of people and say, well, I got this buddy of mine from Lisbon, and I got this buddy of mine from Copenhagen, and this student of mine from Mumbai, and you know, it's a really cool environment to work in, and very international. And we'll talk about that maybe a little bit more. Finding the Higgs, it is as big as they made it out. Okay, I was born in 1963. I'm ancient. Okay, and that is the year Peter Higgs wrote 2 papers describing how if the symmetries of the universe were broken in such a way as to create the forces we see, there had to be created in that process a new particle. He wasn't the only one. There were several others. The French guy they kind of show there, Francois Englert, he and René Brou, who passed away unfortunately before the Nobel Prizes were given out. Englert and Brou also wrote a similar paper. Some people call it the Higgs-Englert-Brut particle. Some people call it the Higgs-Englert-Brut Kimball particle. Kimball-Nambu-Brut, Englert, Higgs. Anyway, it's the Higgs particle. All right, that's what we call it now. There's Francois Englert there. But it was big. I mean, Maclean's, magazine came out. This changes everything, I adore this picture of Fabiola and Peter Higgs. This is the Louisiana Tech Particle Physics Group at the time. Some of these folks have moved on. Katrin Bernius was a postdoc of ours. Matt Tamset, a postdoc of ours. A couple of our graduate students, Ram and Roshiv here, were both at CERN for a year or so. Dick Greenwood, myself, Marcus Wobish, we're all professors there at Louisiana Tech. They didn't show Katrin, but Katrin was office mates with Monica Dunford, who was featured in Particle Fever. So I guess they must have kicked Katrin out to film those scenes. So you can't see any Louisiana Tech personnel, but you can see our computers on the desk when they're showing that scene. So Louisiana Tech. So we've been involved there. So I mentioned that the Standard Model is incomplete. It's this beautiful theory, the most precisely tested theory that mankind has ever come up with. It's just a testament to human knowledge, and we know it's not complete. This is the Hubble shot of a piece of the sky the size of a grain of sand held at arm's length. Those aren't stars. Those are galaxies. Okay? Astronomy, and I'm giving a talk, in fact, Saturday night to the Shreveport Astronomy Society at LSUS. I'm going to come out. Astronomy is, there's BH and there's AH. There's before Hubble and after Hubble. It's that serious. Our view of the universe is so different now than it was before Hubble was launched. And it's given this really cool, but in some ways scary view of the universe that we have now. We know that the universe is 13.7 billion years old. We know that number to about 0.1 billion. Okay, very accurate. The universe begins in this hot, dense phase. It's called the Big Bang. That was a term of derision. The guy who came up with that term didn't believe in it. He actually thought the idea of a Big Bang was an interjection of religion into science, which is kind of funny because now some religious people don't like the idea of the Big Bang. But, so, it's funny how the world works, right? The universe begins and you think, okay, it's a Big Bang and it expands. No, it doesn't. It's a Big Bang and it expands. I mean, I can't go that fast. It expands. Let me try it again. And then slows down. There's a process that occurs between 10 to the minus 34th seconds after the Big Bang and 10 to the minus 30th seconds after the Big Bang. So a very long period of time in which the universe expanded so fast that the pieces of the universe couldn't communicate through signals passing at the speed of light. All right? So sometimes they say it expanded faster than the speed of light. Not really, but it expanded so fast that the pieces of the universe couldn't communicate with each other anymore. And that's called inflation. What causes inflation? Well, there must have been a particle that caused it. What was that particle? It might be the Higgs. So we don't know that for sure, but one of the ways that the Higgs feeds into this is the Higgs may actually be the particle that causes that initial rapid inflationary expansion of the universe. But we know this age now We know the development fairly well. We know that the universe started off being largely something called dark matter. We know that it's now less dark matter and more something called dark energy. Let me come back to that in just a second. How do we know that? Things like the Hubble, right? Looking at distant galaxies, measuring the recessional rate of these galaxies, how far they're moving away from us. The WMAP experiment, the Wilkinson microwave anisotropy probe, had too many glasses of wine. Wilkinson microwave anisotropy probe looks at the cosmic microwave background. This is radiation. It's about 30% of the static you would get on an old-time TV if you put it on a station that didn't have a station broadcasting, just, you know, static. Some of that is actually cosmic. You're actually looking at the Big Bang when you're looking at static. When the astronomers first discovered this in the 1960s, they thought the Soviets were trying to jam our radio communications. It's this microwave radiation that comes from all directions in space. We thought it was uniform for a long time, but in fact there's little fluctuations at the level of about 10 to the minus 4th, 10 to the minus 5th. Tiny little, some people very poetically call it the fingerprint of God. It's these little fluctuations at the time of inflation that later gave rise to things like galaxies. All those little things we saw in that earlier picture from Hubble. So things like WMAP plus telescopes like the Hubble measuring distant galaxies tell us that matter, the stuff that looks like us, protons, neutrons, electrons, make up about 5% of the universe. So this is the part of the universe the Standard Model describes really, really well. We do a really good job describing 5% of the universe. There is 23% of the universe at this epoch that consists of this stuff called dark matter. Ask me what dark matter is. I have no idea. We know it's there. We can see its effect. How? We measure galaxies, rotational rates of galaxies. We see that the galaxies aren't rotating at the speed they should be rotating. Vera Rubin, a great woman in science, Vera Rubin, discovered this in the 1960s. The galactic rotational rates are wrong. But if there's some missing matter, some invisible matter there, then that will correct and tell us. We can actually have imaged dark matter. We see collisions of galaxies where the center of mass is not the center of mass of the stuff we can see. You can go online, NASA, you can see these photographs where they show where the dark matter must be. So we know it's there, we just don't know what it is. Okay. Big deal, it's just 23% of the universe. The really cool thing is this 72% that's a little bit of what Nima was talking about. Nima is pretty well known in the field. I was at a conference with him back in June. He's kind of a jerk. Anyway, but Nima's right. There's this thing called the cosmological constant. Einstein put it into general relativity. General relativity is 100 years old this year, 1915. Einstein comes up with this general theory of relativity that describes gravity. And those of you who've taken calculus, you know that you do an integral, you got to add this constant of integration at the end. Well, that's what the cosmological constant was. It was just, he just put it in. He didn't think it really was a thing. And now it seems to be 72% of the entire universe is this cosmological constant. And it's driving the expansion of the universe to be faster and faster. In fact, the universe is not only expanding, but we now, and literally, less than 10 years we've known this, that expansion is actually accelerating. And that's post-Hubble, very recent science that we had no idea of before. So there's all this cool stuff out there. So how do we go beyond the Standard Model? What are we going to look at? Let me give you some news. Okay, so this movie came out a while ago, post-production, everything. It's maybe 2 years information that you were looking at. What can I tell you? We're going to turn on in 2 months. So like I said, there was this 2-year shutdown. We've been doing these upgrades. We've been upgrading the magnet and the accelerator. We've been doing upgrades to the experiment. We're going to turn back on in about 2 months. In fact, next week, we expect those first beams to start going through the accelerator again, and we expect to see little beam splashes. I was there in February. I'll be back there in April. So we're about to turn back on. That's really cool. We should be almost at design energy, very, very close, because they fixed the magnet problem. What else? Fabiola. who you saw Fabiola Giannata, I love her. She is everything in a bag of chips. She is so cool. My experiment I was on as a graduate student, she was a postdoc. I've known her for years. She is terrific. She is going to be the next Director General of CERN. She's going to be the first woman to be Director General of CERN, the largest scientific organization in the world. And I think that is so cool. So cool. And so we're about to turn back on. The upgrades are finished. We're ready to look for new data, and Fabiola is going to be in charge of the lab. So we're in pretty good shape. What are we going to look for? Again, the movie doesn't tell all the possibilities, but one of the important possibilities, one David Kaplan likes, and I used to like a lot when I was younger, is this idea of supersymmetry, that everything that we see in the standard model has some sort of shadow partner particle, and maybe they're heavier, they exist in this heavier, higher energy world. And that's cool because they're kind of easy to detect. We have these collisions and we see all these tracks and everything. We look for an imbalance in the energy, and that missing energy is then the signature of something invisible, a dark matter-like particle being produced, and supersymmetry very naturally predicts the existence of something that will be the dark matter particle. There has to be a lightest supersymmetric particle that doesn't decay into anything normal, okay? And so it takes away energy, doesn't interact with the experiment. So SUSY would be great, except the Higgs is kind of at the wrong mass. And then you get Nema's idea. Nema's idea, again, is that we're in one slice of some huge, it says megaverse here, he calls it a multiverse, whatever. But it's cool. Things may not be the same everywhere. Everywhere being other dimensions that we can't communicate with because we're in our pocket of this multiverse and they're in their pocket. But there might be forces which in high energy collisions do communicate between those different segments of the multiverse. And so Nema's idea is that somehow we can have these Kaluza-Klein particles, not to get too technical, that somehow communicate what happens in our universe with what happens in these multiverses. That's not that's not the only possibility for extra dimensions. Gravity, for example, might be very, very weak in our world. It is compared to the strong nuclear force or electromagnetism. Gravity is weak. It's a wimpy little force. But it may be strong someplace else. Again, someplace else being a fifth, sixth, seventh, eighth dimension. And what we see in our universe might just be gravity kind of leaking in a little bit. Okay? We can actually test that at the Large Hadron Collider, strange as that seems. It also is possible that the extra dimensions aren't big. One popular theory that we're going to look for is this idea of compactified extra dimensions. And so if you can think of this grid as being our four-dimensional space, okay, so that's not a two-dimensional grid, it's a four-dimensional grid, okay, kind of step back and expand your brains here a little bit, okay? Then the fifth, sixth, seventh dimensions might be curled up in very tiny regions of space-time, maybe only on the size of a millimeter or so. And those compactified extra dimensions are, again, something that we're going to try to probe with the Large Hadron Collider. So there are these extra dimension, large extra dimensions, small extra dimensions, compactified extra dimension theories that we're going to look for. There are also the supersymmetry theories we're going to look for. So how do you talk about particle physics on date night? I don't know. I think she thinks that what we're doing now in these experiments really is the crowning moment, the crowning achievement of a search that goes back to Democritus and Lucretius and the ancient Greeks of trying to understand what our universe is made of. But of course, she's more the theorist, right? He's more the experimentalist. He really thinks that what we're doing is international collaboration. I mean, this is so cool. On my experiment, I have colleagues who are Israelis working with colleagues who are Moroccans. All right? I have colleagues who are Japanese working with colleagues who are Chinese. Americans working with French. I mean, it's this amazing. That was supposed to be a joke. All right. So this huge, amazing collaboration from literally from all over the world. I'm gonna 8 o'clock in the morning. I'm gonna be on a video conference. The main players there are one guy's from England, one guy's from Portugal, one guy's from the University of Chicago, one guy's from Louisiana Tech. You know, it's strange, but it's cool. And it is a real model of international collaboration. And I think it's something we can all be proud of. So Lastly, I mean, if there's any takeaway, a couple of graduate students, I gave a TEDx talk and they loved the slides, so I put it up for you. Knowledge changes people, right? When we get along, we can do these things together because as we learn about nature, sort of our petty differences don't matter as much anymore. So, thank you for hearing me expound on my soapbox. Ask me anything. Please stump the chump.
That would prove the supersymmetry theory correctly, and if it was different mass, then it would prove the multiverse theory correct.
Right.
Since the film was published, have they made any progress on discovering if it's a different theory or?
Excellent question. So since the film was made, we gathered more data. We have better statistics. We know the mass of the Higgs more precisely. It really is right there at that 125. If you remember them talking about sigmas, we were at 5 sigma for discovery. We're now at like 8 or 9 sigma. The Higgs is there. That's the mass. It's around 125 GeV. You're right. In the models that we have so far, remember they're models. I love nature. Nature's so cool because she comes up and she says, hey, you want this theory, that theory? The heck with you. Well, I'm going to give you this one, you know? I mean, so it's right there in the middle. We say it's metastable. It's metastable. In other words, at 125, the Higgs will decay, but we don't know when. It could be so long-lived that its lifetime is longer than the lifetime in the universe. But we don't know yet. And so there's a lot of possibilities that open up in May when we start back up. How do you guys want to work back? Maybe right back here, because that's closest to the mic. There we go.
I just had a quick question. I noticed that there were 4 impact sites for
Yes.
They weren't evenly distributed. Why those spots? Is there significance to that?
No. I'm worried a little bit that was just perspective on how they were kind of looking at the ring. Nevertheless, LHCb is closer to Atlas than it is. There's actually 8, so let me take a step back. There's actually potentially 8 spots where we could have beams collide, okay? But for in terms of just really money, really, they chose only 4 to have major experiments. And I think they try to keep them as close as they could to the main CERN site as possible. So you're right, ALICE and LHCb are fairly close to where Atlas is, and then CMS is way over there on the other side of the ring. And at some point, then it's balancing the beam dynamics. If you're going to have all these guys here, you have to have the other guy way over there on the other side. We could have up to 8.
I was just curious. You mentioned that Higgs particles give things mass.
Right.
But gravity is the warping of space-time because of mass. So how does the Higgs particle work with general relativity? Does the Higgs particle warp space-time, or how does that work?
So, oh wow. Well, you know, I'm so embarrassed you asked that question. I'm going to get my student over here to answer instead. No, that's an old Einstein joke too. There's mass, and then there's the coupling of things to mass. Let me take a step back. The Higgs has to do fundamentally with breaking of supersymmetry, or symmetries rather. When the universe began, that hot dense phase, there was symmetries there was no 4 forces of nature. There was just one force. Everything was massless. There was a single force in the universe driving this inflation. At some point, it's like balancing a pencil. You know the pencil is going to fall, but you can't predict what direction it falls. But once it does, then you know, boom, that's the direction. At some point, that symmetry broke, and some particles picked up mass, and the others didn't. That mechanism by which the particles that became massive picked up mass is the Higgs. Now, farther down in the evolution of the universe, gravity starts kicking in. And then gravity couples to those masses that have been created. So the Higgs, if you want to think about the Higgs field and the gravitational field are 2 different fields that act on mass. Now, gravity is weird. You have pointed out the most fundamental problem in particle physics right now, and that is general relativity at large scale, cosmological gravity, and field theories, what happens in subnuclear gravity, don't match up. We have no good theoretical model of gravity that can match up general relativity to the subnuclear. That's what people like Dave Kaplan and Nemo work on. One possibility is superstrings, that these fundamental particles are not point-like, but they have some length that actually exists in 11 dimensions, or maybe more, maybe less, depending on who you talk to. Right, there are these possibilities, but they haven't been proven yet. That is gravity is the fundamental problem. And so when I talk about the standard model being well tested, that's a model that is three of the four forces: electromagnetism, strong nuclear force, weak nuclear force, but not gravity. And we want to get gravity in there. Yes, ma'am.
Okay, I have two questions actually. Okay, first question. Earlier on in the movie, they were talking about what they were expecting to find when the beams collided,
Right.
and they wanted to find lots of different kinds of particles.
That's right.
So was the Higgs the only thing they found, or did they find other stuff that's just been overshadowed because the Higgs was such a big deal?
So we have found other particles, but they weren't cool.
They weren't cool.
Okay.
Okay, that was
So, you know, they were talking about in the 1950s and 60s of this huge plethora of particles. And that was true, you know, particle a week sort of thing. These are composites of quark composites, you know, different kinds of quarks. And we've discovered some particles like that, these composite type systems. We've made some very fundamental discoveries in terms of nuclear interactions, looking at what's called quark-gluon plasmas that form at very high energies. But in terms of a fundamental new particle, like the Higgs, so far it's just, that's it.
Okay.
So we're hoping.
Okay, so that leads to my second question.
Yes, ma'am.
I have mostly a chemistry background, so I understand things on slightly larger levels with protons and electrons and things like that. Everyone,
Yeah, that's all just electromagnetic force.
yeah, all that stuff. But everyone describes, when they start talking about particle physics, all they talk about is, oh, quarks form up protons, and that's all I get. So what about the rest of the particles? What are all these other particles we talk about that people are finding, other than photons? I've never heard of anything.
Okay, so yeah, the quarks and the force carrier, the gluons, form things like protons and neutrons, right? The W and Z particles, those carry the weak force. Those cause beta decay. You have a chemistry background, radionuclides. Beta decay, weak decays. It's also the force that drives the sun. So the fusion process in the center of the sun is through this weak nuclear force that's mediated by these W and Z bosons. So that's kind of important because that's why the sun shines. You are in a sea of neutrinos. There are millions of neutrinos passing through you every instant, produced in the sun. They mostly don't interact, and so they're not a problem, okay? But neutrinos are actually the most abundant matter particle in the universe, and they're washing through you right now. But that's it. I mean, we have the quarks, electrons, neutrinos, and then for some reason nature decided to make two heavier copies of those. And why do we have those three families of particles? Again, one of those open questions, like gravity. Did I answer your question?
Yeah, pretty close. Thank
Okay.
you.
We got one there, and then
One more
I
back here.
think we'll take some
You got one more back
discussion in the lobby. Yeah, go ahead.
So, okay, so with the GeV measure of 140, that's the like unstable multiverse,
Right.
and then 115 would be the
Susie.
supersymmetry.
Supersymmetry.
So at 125, does the GeV measure like determine the rate at which the Higgs particle decays?
No, like I said, it's metastable. We know that that's at a mass where our models predict that the Higgs would decay, but no, at 125 we can't predict.
Is that
Yes.
was that like the pie chart in a few slides back when it had like dark matter at the universe's creation, and then present day it's all like dark energy, and we don't know what that is? Is it like being converted?
So yes, the dark energy component of the universe doesn't kick in until after the galaxies start creating and start expanding away. Before that, gravity dominated. So early in the universe, actually gravity was the strongest force, and then when all these symmetries started breaking, gravity appears to have become weaker. We don't know why. But
Does that mean there's like an end if it decays.
How will the universe end? It's possible that we live in a charmed era. If the universe expansion really is accelerating, there will be a point several million years from now where our descendants won't be able to see other galaxies because they will have moved so far away and their light will have redshifted so much that it will no longer be visible. So several tens of millions of years from now, our descendants will see a dark sky without any galaxies. We live in kind of a charmed epoch. And then as they get farther and farther apart, well, this is where the models aren't too clear. Some models say we have a heat death of the universe. Some say the universe kind of cracks and dissipates. If there's this if Nema is right, Nema's the devil, okay? So if Nema's right, then we're a bare bubble in this big foam of the multiverse. And about 10 trillion years from now, that bubble just kind of dissipates.
We got our last
Sleep
question
well!
here. Last question.
Okay. So my question is all sort of tied into what she was saying, and that is, we recognize that we have the 126 whatever units.
126 times the mass of the proton.
Yeah, that. The Higgs. Okay. Are there other types of Higgs that we are possibly looking for? And if so, are any of those more or less the stable kind, whereas we don't have to worry about them decaying?
I love all of you. These are great questions. Yes! Susie, again, if Kaplan and those guys are right, Susie predicts, in fact, that there will be 4 Higgs. There'll be this one we've seen, a heavier neutral one, and 2 charged ones. So, yes, there may be other Higgs that we discover. And that would prove Susie right off. Boom. If we can find another Higgs, then it's a Susie kind of model that's the explanation for the missing pieces of the standard model.
So the higher speed is next time.
Right, we're doubling the energy. We're going from 8 trillion electron volts in our collision. That's about like 2 trucks colliding, only it's protons. All right. We're doubling that energy. We're going to 14, well, maybe 13 and a half. 13 and a half or 14 TeV when we start back up in May.
Now, what's the max power that it can convert?
That's the design energy. 14 was the max. So after that, we just try to increase the brightness of the beams.
Well, I think I really want the audience to give themselves a round of applause because that's just fantastic. We are just absolutely thrilled that we got a full house on Monday night, and I'm just going to give all that credit to a wonderful supporter of the Robinson Film Center, Dr. Sawyer. Let's give him a hand. And let's do autographs in the lobby. All right? All right, good.
Thank you.